So I don't know that means how many from which batches have joined, because I think the total class size should be around 80. So it's almost 50%, I think. Is anyone joining more? Please inform me. Or I don't know that means why this because I don't know why this happens every time. Okay, if something is posted to the Google Classroom, I think you all should take care of that. I don't have to repeat. Okay, so please all the CRs have joined for the 3 batches. Okay, they just confirm that no one else will join, so that I can start the class, because it's very difficult for me to give the admission in between the class once I start the class. Okay, so as there is no response from many of the CRs, so I accept that what I said is okay. So I will not make entry to any other to the students who will be coming from now. Okay, so make sure it's okay. It's your class, right? I am just facilitating you to learn the subject. Okay, and if you are at this age, if you are not able to respond to Google Classroom or this being a students of IT, electronics and computer science, right? I don't know. That means what next I can do. Okay, so let me take the class. I have taken the class, okay, though it's a formal holiday to the university, but you know that this particular course is a bit heavy course, right? And we need to have the lectures. Actually, more lectures than what is required. Okay, scheduled. Okay. So I thought I will take this class online. Okay, the next class will be physical. Next class will be, I think, what's the schedule? Next class is 29th, on the day when we are opening after the holiday, and 29th, so there will be physical class. 5th, there will be physical class. 12th, there will be physical class. So I hope that within this next 3 lectures, I will be able to finish my lecture course. Okay, and then if some revision is required, I can obviously go for the next week 19th. But I think from 26th for BTech courses, BTech students will have their exams on early December. So maximum I will take the class up to the next 3 classes. I will take next 3 classes, okay, on 5th, 12th, and 19th. And okay, I will take the class on 29th, 5th, and 12th. Okay. Yeah, so that's all. So that's the plan of the class, ending classes. So after today, I think I will discuss, today I will try to discuss about this digital filters, which we started in the last physical class. Okay, what happened, I think, 15th or 8th, sorry, no, 15th I was not there in the university, I believe. So it was 8th. So physical, so last class was on 8th of October, okay. So today I will discuss a digital filter. 29th I will discuss about the DSP processor. 5th I will discuss about the GPUs. Okay, we will go into the, and maybe 12th I will just give you an overview of what are the applications we are doing and what are the projects you can do. Okay, from this particular course. Okay. So let me start my lecture today. Okay, so I hope that we finished Z transform in the last lecture class on 8th of October, right? And we started the introduction to the filters, not digital filters as such in a depth, but we tried to discuss about the filters just to motivate you that, okay, why it is so important and why design of filters are required. Okay, so yeah, so my question is, anyone can let me know what is a filter? Any one of you from the class, can you just explain me? It is already explained in the last class what is the filter. Okay, because I want to set the perspective for good, so that you all know that what we are discussing today. So just to make the initial thought process going. Okay, so what is a filter, or what is a digital filter? Any answers from you? Yeah, Ayush, please go ahead. Yeah.
Sir, hello?
This is a little bit louder.
Sir, am I audible?
Yeah, now we're on. Please go ahead.
Okay, so sir, in a digital filter, we essentially have a pass band and a stop band. The pass band is made up of frequencies that the filter allows to pass through it, and the stop band is made up of frequencies which the filter greatly.
Yeah, good. Yeah, better to tell that those frequencies will go for a sort of an amplification, and the other frequencies will go for an attenuation.
Yes, sir.
Okay, so the pass is a okay. Yeah, so the pass we colloquially tell pass, but pass is something which is a sort of a physical process, but this is a signal processing process. So whatever filter is also a processing. We have to accept it, right? So yes. Filter, digital filter, or filter, the digital filter or electronic filter is also processing of the signals. Okay, you cannot ignore that. You cannot say that, oh, digital filter is something that which doesn't process the signal. It is also processing. But processing of the signals are done in a very discriminative way in a digital filter. So some of the frequencies are amplified. Okay, amplified means their amplitudes either becomes 1 or becomes some multiplier of 1. Okay, maybe 1x or maybe 4x, 3x, 5x, depends what you set the gain of the filter. But the stop band of the filter are those frequencies which are being attenuated. So this processing of a digital filter is a sort of a processing of a wideband signal into a discriminative processing depending on what is the filter characteristics. If it is a low pass filter, it will attenuate the frequencies after a certain frequency, and it will amplify all the frequencies up to a certain frequency of the entire band. Right?
Yes,
so that frequency is called the cutoff frequency, right? Up to which the filter amplifies in the case of low pass filter, and the frequencies greater than the cutoff frequencies are all get attenuated. The same thing happens in the inverse way in a high pass filter. In a case of high pass filters, the frequencies which are higher than the cutoff frequencies are getting amplified, and the frequencies which are lower than the cutoff frequencies are getting attenuated. So attenuated means we can best assume they all converted to 0. Okay, right? Yes. But it is not 0. I have shown, if you remember the previous lecture, the ideal is 0. Okay, but the actual is a rolling off. Okay, is a rolling off amplitude. Okay, the rolling off amplitude, something, it starts before the cutoff frequency, and it just becomes a sort of a mid gain into the cutoff frequency, and then it rolls off slowly to 0. Okay.
Yes.
Okay, so those are the high pass and low pass frequencies, and there's a band pass which has 2 cutoff frequencies. which means that within a wide band, it actually amplifies the frequency from the lower cutoff to the higher cutoff. And before the lower cutoff, everything is attenuated, and after the higher cutoff, everything is attenuated. So only between two frequencies it gets amplification, and that's why it's called a band pass filter. Okay, so we have to accept that digital filters are also processing signals. It's not that there are signals are not processed, but signals are processed discriminatively based on the frequencies. And when we tell signals, actually it's not signal, because signal is basically a continuous signal property. We will try to appreciate that. We have already studied that the continuous signals have been converted to samples, and there is a discrete Fourier transform by which we can identify the components of my sample window, right? We know that what are the H0 to Hn. Okay, where H0 is the lowest frequency component and Hn is the highest frequency component. Okay, okay. Because why? Because the transform introduces e to the power j omega n. Okay, where omega is a frequency and n omega is basically the multiplier. Okay, so when we go higher values of n, right, it will be higher and higher frequency coefficients we are generating. Okay, so that's the way we are actually telling the frequency, the frequency components of a discrete sequence. Okay, and then we tell the digital filters which processes the discrete samples but selectively based on their frequency coefficients. So the frequency coefficients which are high frequency or low frequency, depending on the low pass, high pass, or band pass, will be attenuated and some will be amplified. Okay, so am I clear to all of you on this? Anyone has any doubt? Everything is processing here. We haven't introduced the digital signal processor still, but we are trying to make you aware of the fact that everything here is processing. You have to, starting with the initial sequence, right? You have to do computations, right? In terms of additions, multiplications, in terms of complex exponentials, right? All these computations you need to do. Okay, and the mathematics, okay, which govern these computations we are learning. And we all know that ultimately there will be some sort of processing hardware, okay, or a processor, which can be a very naive processor like a normal ALU, or it can be a little bit different processor which has a MAC ALU in the DSP processor, which helps you to compute this faster. And we will learn pretty soon, maybe in the next class, after we finish the digital filters today. Okay. So we are now still learning the computations. And intermediate, we have learned the Z transform, and that helps us to actually just to give Z to the power n order. We are not actually going to this exponential complex variable mathematics. We are trying to understand everything in terms of Z transform, and that makes our life easier in terms of the computations we do. And also we have learned in the Z transform in the previous lecture, which was on 8th October physically. Okay, we also learned that this Z transform also helps us to understand the stability of the system. Okay, the region of convergence, to identify the region of convergence, and to try to find out the properties of regions of convergence, which are well defined in the Z transform. Please have a relook on the Z transform. And from that, we know that we first of all find the region of convergence, and then trying to find whether Z is equals to 1 within the region of convergence or it's not. We can define that whether it is stable or non-stable, right? And there are the other properties also which we discussed in the previous lecture. So these are all the things what we discussed until today, okay, before the start of this class, okay? So I'm again repeating that we have covered a good amount of the course, okay, within the, we have almost, I think, completing 10 or 11 lectures, maybe more than that or something like that, okay? But I'm telling that there are a lot of topics being discussed, okay? So I think you have maybe the MSc students have maybe 1.5 months more. BTech students have maybe 1 month more to start the exam. So please, okay, please go on studying it. If you are missing anything out, please come back to Google Classroom, right? Ask questions, okay? Okay, so that you are all prepared before you complete this course. Okay. So let me start my presentation today. Any questions any one of you have on the things what I discussed just now, or anything which was already discussed in this course? Anyone has any questions or anything to clarify, anything to get cleared? I know that I don't know that how much you are studying this course, but I expect that you will be giving the proper attention to this course, okay? This course is very important course to understand you the real signals, okay, what you will be processing, and to understand the mathematics which are used of processing those real signals in the discrete domain. And that's what is major computation. Major computation at present are the things what are being captured through IoT. Okay, what are the things which are captured through your sensors? Okay, you try to reduce your computational power in deep learning and all these applications. So all this comes into understanding how the real data is being processed and what are the underlying mathematics of processing this data. And this course gives you the perfect information or perfect knowledge to handle the data at that level. Okay, so that's why this course is so important. Okay, so I hope there is no questions further. So let's go to my lecture. PPT, I will just check whether it is already uploaded or not. But let me check it. I will just get back after the class and check it in the Google Classroom. Oh, no, not this one. Okay. Is my clear? My presentation is clear.
Yes, sir.
So this is what is the summarized scenario of digital filters. Okay, so we have signals in the real domain, converted to digital samples through ADC. Digital filter is a processing, as I said, but discriminatively processed. Means the samples are processed, okay, as per the frequency response of the filters, okay, and then whatever is the processed output from the filters, it is converted back to the continuous signal through a DSP, digital to analog converter, because many of the real life actuators works in analog mode. Okay, right? If you are driving a stereo speaker, right? Its output is analog. It's a continuous vibration, right? Right? If you are moving something, oscillating something, right, it is a continuous movement. So ultimately, the output needs to be analog in many of the cases. So this is the picture. So any confusion in understanding this picture? Anyone? Tell me. Okay. So what digital filters actually does? Digital filters, as we discussed also, okay, in this class today, that it tries to discriminate the components in terms of its frequencies and does the processing as per the nature of the filter. Okay, high pass, low pass, band pass. Okay, there are band stop filters also, where it means that a particular band intermediate, okay, just the inverse of the band pass. So it passes, so band stop passes everything except a particular band. Okay, and there is something called notch filter, which is also a band pass filter, but which has a very close, the upper and the lower and upper cutoff frequencies are very close. So instead of a good valley of a band pass filter, it just have a sharp peak in the band pass filter, which means it's a notch filter, means a particular filter having a very narrow pass band. Okay, it's called a notch filter. Okay, so let's move into the applications. We discussed many things: audio processing, generic signal processing. Any IoT signal gets captured, data gets generated, right? You have to go through this. Okay, image processing. Image is basically mostly it is a sensor driven application. Unless you have a camera, either it is RGB or it is thermal or it is multispectral, right? You cannot start processing. So basically, any image you require a sensor. It's called an image sensor. Okay, which actually that means absorbs. Okay, or actually, yeah, that absorbs the intensity. Okay. And biomedical engineering, lot of fluctuations of our body parameters, be it the ECG signal, EEG signal, be it the blood flow, be it the image scans. Okay, all the way it requires the biomedical. All the way it requires the digital signal processing. Control systems, automobiles, right? That means electrical controls, robotic controls. They also work on the different signal components and signal channels which they take, and based on that, analyzing those signals, they decide what are the control instructions to be given. Okay, so that are the industrial applications, that the manufacturing, okay, robotics, okay. All this real data which are generated are ultimately being analyzed and being taken selectively by the filter. So filter is something in a other way. Filter is something by which we can capture data selectively. And this is also important. This is also important why filter is so much of prominence. Okay, if you want to capture a particular intensity of light or a particular wavelength of the light compared to the other, you see when you go to the advanced cameras, they give different options. These options mean they are playing with the wavelength of the light, what you want to have more or what you want to have less. Some wavelengths of the light you can have less, so you are stopping those using the filters. Some wavelengths of light you want to have more, so you are amplifying them. So they are now into the pass band of your filters. So accordingly, the filters get adjusted. right? And this wavelength is there for any electromagnetic spectrum. Though for the light it's visible, but for any electromagnetic spectrum, there are wavelengths. Okay, be it a temperature, temperature radiation, thermal radiation, where we capture the temperature. It also has a wavelength. Okay, the thermal radiation works in a wavelength band wavelength. So you can pick a particular band of the thermal radiation, right? Similarly, in the case of audio, right, you can actually take a particular frequency of the instruments, range of frequency of the instruments, or range of frequency of the speaker or the musician, of the singer. So lot many things. In the case of industrial, you can take a particular signature, thermal signature or acoustic signature of an instrument or of a process, right? And how you take a particular signature, because you are now focusing on a particular wavelength, right, or a frequency spectrum, and for that you require the filters to do that work. Okay, so I hope the applications are well, though we cannot practice the applications due to the limitation of this course. This course doesn't have any practical course. It's but I think any point of time you want to do anything, all of you have at least 1 or 2 semesters there. Any one of you have an interest to do something with some of the things are there in my lab at my department, right, we can do something. So let's move on. Any questions on these applications? Any one of you? If you have any questions, let me know. So any questions, anyone, on these applications? Yes, no?
No, sir.
Okay. Now let's start with, I think I started with these two, FIR and IIR, so FIR, fundamentally there are 2 types of way we can design the digital filters. It's not based on the pass band or stop band or something, right? It's based on the way we can design the filters. So the filters, digital filters, can be designed in 2 ways. One is called finite impulse response, where it depends the output. I discussed already, I think previous class I gave a little bit intro on that. So the output, the current output of a digital filter, if it's an FIR, you will see that the terms included in representing the output of this digital filter consists of only the current and previous input values. Only the current and previous input values. The output values are not included as an input. Previous output values are not included as an input. In the case of FIR, it's only the current and the previous inputs. So the entire output just goes forward, just takes the current and previous inputs. No feedback, no input from the previous output. So no feedback, no memory. As such, there is no memory in the feedback path, And it's a stable, it's less complex, and it's a sort of a moving average filter, which means that it moves over a window, right? And does a particular averaging over the window, right? So averaging over moving average filter is called a moving average, or it's also called a filter, because moving average is a sort of a low pass filter. When you average, then what happens? The high values and the low values. Normally, the high values gets largely reduced in the average. So it's basically a low pass filter. So So doing a moving average. Moving average means you are actually representing a bunch of samples with their average values. So the noise, so the difference between all the values gets reduced. And this is not done over the entire window, but we do within the subsets of window. And that's why it's called the moving average. So it first goes to the first subset of the samples and replaces all the samples by their average, by the average within that bucket. And again, it goes to the next bucket of the samples. Again, it replaces all the samples by their averages within the bucket. So that's called the moving average. Okay. So the output only depends on the current and the previous inputs. Okay. But the other type is called the IIR, infinite impulse response, where the output depends on the current and previous inputs, but previous outputs too. So this is an extra component which gets added in an IIR filter. Current inputs, okay, current input, previous inputs, as well as previous outputs. And that makes the feedback, and that makes the things very complex, and that makes it less stable, okay? And the examples are Butterworth and Chebyshev filter. These are also types of filters, okay? So we'll go to the mathematics and the design of these filters, but just the basic properties of this FIR and IIR filter, okay? So any question on this slide? Any one of you? Any one of you has any question on this slide? Yes, no, I want to listen.
No, sir. No, sir.
Okay. So, as we know the filter characteristics, if you like to look into the filter characteristics, okay, so we already discussed this. One is the pass band, one is the stop band. Pass band are the range of frequencies which are passed through, which actually means that they are being amplified. And stop band, which are frequencies which are attenuated. Means pass band means amplified. The lowest amplification is 1. It means that it remains the same, and it can have a high gain also. Okay, but the stop band frequencies are attenuated. So whatever was the amplitude, it goes much below than that once I pass it through the filter. The stop band frequencies. Okay, and basically the order of the filter is dependent on the number of the samples we are trying to take. Okay, it basically depends on the window size. Okay, but you can also define the order in terms of the coefficients what we try to add up with. Okay, we'll come to this very soon. And stability, as I know, the stability of a digital signal processing system we discussed long ago. It's called a bounded input, bounded output, and we already know what's the bounded input and bounded output. So if the input is within a bound, means within much less than infinity, the output should also be much less than infinity. Okay. So and this is basically a stability issue is there in IIR filters. Okay. The design parameters are cutoff frequencies. In case of high pass and low pass and band pass or band stop, what are the what cutoff frequencies? The sampling frequency, the rate of which the signal is sampled, and the filter coefficients. As I said, filter coefficients are very much important characteristics to define that, to design these filters. Okay, so when we try to design the filter, okay, what we need to know the pass band and stop band, and what we generate the cutoff frequency, the sampling frequency, and the filter coefficients. We have to settle this out so that we can design the filter properly. Okay, the sampling frequency defines a sort of the filter filter own H value. We know what is the H value. H value is the system transfer function. Okay, so cutoff frequency and sampling frequency, okay, together defines the system parameters of the filter, right? And we'll come very soon on this. So let's try to come and try to discuss a little bit in details about our FIR filter. So this is the FIR filter, which is expressed by the equation like this. Okay, who can explain this equation? Who can explain this equation which has been given here? Anyone? Because this equation we have discussed in different ways in our digital processing. Might be convolution, right? But this is now being discussed in terms of the FIR filter. So anyone can explain. Already the explanations are there, but still, if you want to, okay, so tell what we are doing here. We are generating YN, right? And what is YN? Who can explain this? All the terms. Anyone? Any one of you can explain this term, equation? We should try. Yeah, please go ahead.
Sir, basically this is a convolution of the input signal with respect to the frequency impulse response of the system that we are using. And YN, sir, is
system, this is a filter. We were discussing in terms of the filter. So the system is a filter, digital filter. Okay.
Yes, sir. So, sir, here the impulse response signal is constant, and we are flipping and sliding the input signal and performing.
It's a HK. HK is also a sequence. The impulse response is also a sequence.
Yes.
It's not a constant value like 5 or 6 or 7. It is an HK. Means as we change the value of K, the HK value will also change. But it's also a system. It is defined in terms of the system transfer function of the filter, which is also called the filter coefficients. So yes. If you look into this, so how many of you have done convolution in the deep learning? So deep learning convolution, if you look closely, it's something like that, weight multiplied by the inputs, because xn minus k means we have to, for generating yn, okay, depends on what is the length of the k we take. Okay, right, that's the order of the filter. Okay, so if we take the k up to length m, means we are multiplying h0 with xn, h1 with xn minus 1, h2 with xn minus 2, and hm minus 1 with xn minus of m minus 1. So those many x values with corresponding h values are being multiplied and summed to generate yn, which is similar in a neural network. If you look in a neural network, it's wi cross xi. Only there the xi was not a part of the same sequence. Okay, xi is a part of the, here xi are the time spaced samples. But just giving you a hint, if you go to the image domain, I think many of you do convolution on the image. Okay, the axis becomes space in the case of image. And then what you do a patch operation where wi is multiplied on the neighborhood patch. And that neighborhood patch is nothing but the samples which are on the spatial neighborhood Here it's a temporal neighborhood. Xn minus 1 is just the previous sample of Xn. Xn minus 2 is just the previous sample of Xn. There it will be from a central, it will be X, okay, I minus M, J minus N. So this is a two-dimensional and it is spatially ordered. so very similar things, okay. So basically a convolution is also a filter. A convolution operation is also a filter, which is very exactly the same properties what we have a digital filter. So this is why I'm telling that these fundamental maths is so important to understand what you are doing in the many of the present high complex stuff. Okay, let's come back to the digital filter. I think you have explained quite well, okay, right? And that's what exactly is that. So we try to generate the terms yn. So once we generate the terms yn, how we will know that yn is a high pass, low pass, band pass? Who can answer this question? Because yn is the ultimate output, and this output should reflect the property of a high pass, low pass, band pass, right? So how we will be sure that this is doing this? So any idea how this expression is generating? Yeah, please go ahead.
Sir, I think we need to design the impulse response of the filter in such a way so that it manipulates the input signal to pass the low frequency, high frequency as per our desires. Because, sir, we can only change the impulse response term here. The input sequence will be generated by the system, and the output only depends on the impulse response.
Right. So very good answer. So this Hn will be a frequency dependent HK. So we have to design this HK such that if we are trying to make it as a low pass filter, then corresponding to the low frequency components, H value will be high, and corresponding to the high frequency components, H value will be low. And it will be just the reverse when we do the high pass filters. Then for the high pass filters, for the low frequency, so we have to go into the frequency domain, okay, that means frequency domain analysis of H. And in that frequency domain analysis of H, we will make the H selective such that it defines the filter what we are trying to design. So in another way, determining the filter coefficients HK will define the filter nature of the filter which I want to design. And that's why H is called the filter coefficients. Is it clear to all of you? Why H is called that? Because this expression is a very generic expression. It is done, but the H gets changed depending on the type of the filter and depending on the frequencies from high to low frequencies. Okay, frequency coefficients represented by the Fourier transform of H or Z transform of H, and then we define the H. So that's why H is called the filter coefficients, which determine the different properties of the filter. Okay, am I clear? And M is the filter order, means up to what length you are actually capturing this window. If you are capturing this window, large window, it's called the large, is the high order filter because you're taking more terms. And if your window is small, it's called a low. Okay, it's called a low order filter. Okay. So is this clear to all of you? Any doubts? Any questions? Any one of you have any doubts or any questions on this? Yes, no?
No, sir.
I just want to listen. If you're all clear with this. Please take a note also what I am telling, because this will not be there in the book. And the problem is that I don't have the time to write a book. I have prepared the content for my students, but I don't have the time to write a book. Okay, because a book on this domain will require a lot of effort, a lot of time. I don't have the time now due to all the research assignments I have at present and teaching assignments I have my present. Okay, yeah. So tell me, so because this way you will not get in many of the books. Okay, so it's better to take a note of what I am, that when I'm discussing, take a note of that. Okay, so I hope this is clear. So now if I want to design this, okay, can you appreciate that this particular type of a functional hardware, because it's not a exact hardware, okay, it's a functional hardware, means you know what are the functions to be implemented in the hardware or in the system. But can you appreciate that this equation and this hardware is same? Who can explain why these two are same? Anyone wants to try? So anyone wants to try? What is this diagram? Can you correlate this diagram with the equation what I have shown?
Sir, can we see the equation once, please?
Oh, equation was just in the last slide, in the previous slide. Okay. This equation and this functional hardware. This design and this equation, whether you can correlate. Anyone else?
Sir,
Please go ahead.
sir, the K0, K1, K2, these are the HK.
Perfect. So see, HKs are nothing but the sample values. HK is also a sample domain. So you can assume H0 is K0, H1 is K1, H2 is K2, because you see the M is there. Km is there. What it means? It means that it is actually from that actually it should be M minus. That means if you try to make K0, it is better to make it K1 actually. Okay. So yeah, so some value of M. Okay, that here small m is equivalent to capital M minus 1. Let's take it like that. Okay, small m is nothing but capital M minus 1. Okay, and then it gets solved. Okay. Okay, now what is this Z minus 1, Z minus 2, Z minus all this? What is the Z minus 1? If you remember Z transform, if your Xn is, that means whatever you have, if your Xn is z minus n. Then your xn minus 1 is z of minus n minus 1. Okay, minus. So what it happens, you actually add a z minus 1 for each delay. Okay, so z minus 1, if you remember, okay, actually z to the power minus d is n minus d. Right? If you remember. Okay, so that means that if you want to create xn minus 1, xn minus 2, xn minus 3 from the tap points, that means for the xn minus 1, you have to cross 1 z minus 1. Xn minus 2, you have to cross 2 z minus 1 because 2 z minus 1 gives a delay of 2. Xn minus 3, you have to cross 3 z minus 1. Xn minus m, you have to cross mz minus 1s. So that's the way the hardware has been designed. And it is hk x n minus k. So here it is km x n minus m. And so you have a multiplier. So you have a, okay, for the first it is a, and it is a continuous adder. So the first adder adds xn into k0 means h0. So the first adder is h0 plus each one xn minus 1. That addition gets added with xn minus 2 h2. That entire addition goes goes continuous addition. Then it gets added with hm xn minus m. And that is yn. All these continuous addition, multiplication with the h coefficients and the delayed x in different forms, in different sequence, generates this yn. Is it clear to all of you? Now this functional diagram is clear to all of you? Yes or no?
Yes.
Good. I hope to all it's clear. It's not only for you, okay? This is the expression. Now we just try to change some terms and try to make this expression as I is equal to 0 to m ki dot x n I. And this is what is the hardware. And you can easily convert it into a hardware, this particular functional block, okay? And now let's look into the way how we will define the hk. So to understand the hk, we have to first come into the understanding of h e to the power j omega, which is actually the Fourier spectrum of hk. And that we all know how to do it, okay? Using the standard Fourier, right? And so, as we see h e to the power j omega, so h e to the power j omega, if it is a, in the case of passband, h e to the power j omega for those frequencies of the passband should be 1 or greater than 1. And for the stop band, h e to the power j omega for those omegas will be much lesser than 1. So it goes for a maximum attenuation. Okay? So now let us design a FIR design example. What we show here is that FS, FC, filter order 50. So which means that capital M is 50. Okay? And cutoff is 2 kilohertz, if 8 kilohertz. So the normal way to design is that we first try to construct the filter coefficients. And the filter coefficients, we try to design, it's called the HDN. Okay? This is a particular nature of low pass filter. Why, if you see, for for n equals to 0, it is static. It's 2fc by fs, which is static. But for n greater than or equals to 0, this is something by sinc function, right? right? And this thing function, we will show that as the value of FC increases, okay, this particular function decreases. The value of HD decreases, okay? And this is the way it is done. So we also apply an Hamming window, which is a sort of a, what I can say, it's sort of a decreases the H with frequency. So this is defined as an omega n and something like this. So that when we have a higher order n, okay, this particular cost term becomes higher, and so 0.54 gets a, that means the 0.56 dot cross becomes maximum, okay, sorry, yeah, that means it's a low pass frequency. So when n is 0, okay, when n is 0, Wn is very low because it's almost 0.54 minus 0.46, which means Wn is very low. So Wn is a sort of a factor which works on HDN. So if Wn is very low, then Hn is very equivalent to HDN, which is the normal. But when n is very high, then what happens? Okay, this the cost term becomes 0. Okay, very high value of n, okay? And then this 0.46 becomes 0.46, 0 becomes 0. So Wn becomes pretty high. Okay, so for that, okay, so you have to understand that, okay, that means HDN becomes, okay, HDN becomes pretty, HN, so Wn becomes pretty high when actually n is less, and Wn becomes pretty low when n is high. Okay, and that's why Hn is being modulated by Wn, and this is called a Hamming window formula. Okay, and this Hamming window formula makes the HDN as per the so this Hamming window formula for a low pass impulse response is something like this, and this we try to modulate the Hn with Wn and try to define the Hn such that the low frequency Hn amplitudes are higher, right? And that is the way you will do it, and this is the normally the things which are done. You can just not explaining the maths, you can just get into this and try to do by hand, and you find that how it happens. You got the result. This is a Python script which is being done, right? And you please try it. Please try it in your with your own way, and try to see how the plot works out. You can take a different type of Wn to modulate HDN, okay, and go through it. Obviously, you come up with this study, and then we'll discuss more on this FIR design. Okay, and there is there's a code available. You can tweak the code, you can do the changes and find that how it looks out. Okay, try to come with your own understanding of the plot and all this type of frequency response and all this coming out. Okay, which we want to have as a design outcome. Okay, this will give you an overview that how the parameters have been considered and how it actually looks like when you plot the characteristics of the filter. Okay, and next we come back to the IR filter. In the case of IR filter, as you see, the terms depends on the both X and the previous Y. That's why the difference between IIR and FIR. In the case of FIR, right, your YN was only defined only defined in terms of the current and previous X. In the case of IIR, it depended on the current X and the previous X as well as the previous Y. Right? And that is the nature of the YN. It has two parts. One works with the input side and one works with the output side. Actually, if you try to see, there is a minus loop which comes from the output and gets fed to the input, and the input minus the output, previous output, some coefficient. So this is a coefficient form which you generate which has with the previous output that gets subtracted, and this is the previous, and this is the current input and the previous input get added. So the net goes into YN. And this type of circuit, I'm not getting into this again. You can just go through this and you can understand that why this is a sort of why this actually makes this a thing. Okay. And if we try to make the response of this IR filter, it comes in this way. HZ is it's a fraction, something numerator, some denominator. Okay, so the BK are the coefficients corresponding to the input. The input coefficients comes at the, okay, that means if you do a Z transform of this, actually, if you do a Z transform of each of this, you will come to this. This is a normal filter response. And the BK and AK are called the filter coefficients here, okay? And actually, BK are the poles and right, and HK are the zeros, okay? Sorry, AK are the poles and BK are the zeros, okay? And the poles lie in the unit circle for stability, as we need to do the Z transform, okay? And this is also an example of IR filter design. So this is the form. Example is given. Frequency response, okay? It is also a low pass filter. Attitude frequency is above 150 hertz, while below 150 hertz, all it preserves. Okay, so this is the. I'm just giving an overview of this. So this is the way we try to define the cutoff and all these things. I will try to. Okay, there is also another PPT. Which I will also send it to you. This is a more detailed explanation of how these filters are done, but this you have to go through on your own and study and come back to me with any sort of, okay, that means understanding. I will pass this filter also. I will pass this PPT also okay, as a lecture note in my Google Classroom, okay? So I hope you try to go through these two things. We will have a physical class next week. We will try to clear any doubts which is happening here, IIR and FIR, and then we will move on to the DSP portion. Okay. I will give you 2 lectures to study. Okay, and the detailed workout are there in this PPT. Okay, so that's all from me for today. Okay, and we have given a little bit of discussion on the FIR, IR, their properties, their characteristics, and also discussed that how to design them. Okay, how to design them with some real application values. Okay, right, and so I end the class today. If you have any questions, please let me know. Let me know. So do you have any questions on this? Anything? Anyone have any doubts? Anyone have any doubts or any questions on today's lecture?
No, sir.
Okay. If you don't have any, please go through these two PPTs. I will just check whether all the PPTs are there with you. If not, I will just pass it to today. Let's meet on 29th of October. Okay. Please make a good attendance so that we can discuss all the doubts. Okay. And we can go into the next lecture. Okay. Thank you all. Okay. Take care and happy Diwali to all of you.